Okay, welcome back to Statistics. This is Dr. Kling, and we're going to talk today about proportion tests. That's tests that involve binary data, where you can either have success or failure, and we want to talk about the proportion of successes. For example, suppose the success is becoming a national merit semifinalist. And suppose nationwide, only 1% become semifinalists. We want to find out whether our school gets more semifinalists than the national average. And a challenge with something like that is that when you're doing a proportion test or a proportion interval, the expected number of successes must be greater than or equal to 10. This is a rule of thumb. And the expected number of failures must be greater than or equal to 10. And so we would need, since only 1% become semifinalists, we would need an awful lot of students to make sure that the expected number of successes would be greater than 10. I guess we'd need about 1,000 students or so. So sometimes you don't have a large enough sample size, particularly if the proportion of successes isn't, or the proportion of failures isn't expected to be very high. Okay, so that's that rule of thumb. Let's do a different problem then. Let's say we're going to do the proportion scoring more than 580 on a verbal SAT. And let's say that the national average, the national proportion doing that is equal to 0.43. I have no idea what it is. And let's say we have a sample, we take a sample of 25 students, and 13 have greater than 580 SAT. And let's say we want to do first a 90% confidence interval for the true proportion in our school. And we might want to do a test to see whether our proportion is which we'll call P, is it greater than the 0.43 national average. So these will be two things that we'll do with this data. Okay, so our sample proportion, which we won't have to calculate, is something called P hat, and that's simply the proportion of successes, 13, divided by the total number of trials, or students in this case, 25. And I'll predict that that will be 0.52. Okay, so but let's throw this stuff in the calculator, get a confidence interval, and do a hypothesis test. So we do stat tests. And now what we're looking for a one prop z interval for the first interval. So we're going to skip over the z interval. I don't know really what the z interval is for. I'm looking for the one prop z interval. There it is, one prop z interval. And now we're going to do the number of successes, which was 13. the total number of students, which was 25. A confidence level of 0.9 is fine, and I will calculate. So okay, and we get 0.356 to 0.684. 0.356 to 0.684. That's our confidence interval. Okay, that's a pretty wide confidence interval. It includes the 0.43, so I'm going to guess that we are not significantly different from the 0.43, but let's go ahead and do the test anyway. So we'll go back and do stat, tests, whoops, I always make that mistake, stat, test. Now we've got to go down and find a 1 prop z test for one proportion. There it is. Oh, we have to re-enter the data. That's too bad. We have 13 successes. Oh wait, it was 2 prop. Okay, now I got what I wanted. Okay, so we have a null hypothesis of 0.43. We have x of, we already have our data, and now the alternative is that we have a higher proportion of higher scoring students. So let's put that as the alternative, and we want to calculate, and we get a p-value of 0.18. A z, which is like a z for a normal distribution of 0.9, and a p-value of 0.18, which is not going to be significant, which is what we suspected. So we got a p-value 0.18. Well, wait, yeah. So if it compared to a p-value of 0.05, that's not statistically significant. Okay, so that's the mechanics of a proportion test. And now we could also have 2 proportions. We could say whether if we had a different group of students, let's say 30 students. Let's say this was sample of last year's students, and 17 scored over what was our boundary, scored greater than 580. We could ask whether that proportion 17 over 30 is that significantly greater than 13 out of 25, and we could do, and that would be a 2 prop z test, because we would enter the 2 sets of data. We would enter x1 is 17, n1 is 30, x2 is 13, n2 is 25, and we would compare the 2 proportions. So what do we want to remember here? We use proportion tests. So prop z when we have binary data, and we use t-tests when we have quantitative data. So that's the first kind of thing we have. Then for either one of these, we could have a confidence interval, or we could have a hypothesis test. And finally we have for either one we can do for one sample or two samples. So with proportion tests it's one proportion or comparing two proportions in two different groups. For t-tests it's called one sample and two sample. And then we'll note that one variation on the one sample is the matched pair. So even though it's a pair, and we use the word pair, it's a one sample. You have to go back to that talk and review that. So if you think of this in terms of a tree, a decision tree, you have to decide, first of all, are you using quantitative data or proportions? So quantitative or proportions. Quantitative would be the T methods. Proportions would be this is binary data. If you're using binary data, you would use the proportion methods, the prop methods. Then you want to know, are you doing an interval, confidence interval, or a hypothesis test? And then finally you want to know whether you're working with one sample or two samples. So you could have, for each of these, you could have one sample or two samples. And when we're working with proportions, we call it one prop or two prop z-tests. And I'll stop there.